Section 6.3, the central limit theorem for sample means. Let's look at this example. Imagine a bakery produced cookies and the mean weight of all cookies is 50 grams with a standard deviation of 5 grams. You want to understand how the average weight of cookies in a sample behave. So first, you're gonna take a random sample of 30 cookies and then calculate the sample mean. So we do have a lot of the cookies in here, and I already know the mean weight of the cookies will be 50 grams, standard deviation will be 5 grams. Now, I'm gonna cut this part as my sample, and then my sample size will be equal to 30. I'm gonna measure the weight of each cookies, and then I'm gonna calculate the mean of this part of the cookies, and then I find it out. The sample mean of these 30 cookies will be 49.2 grams. Now, I'm gonna do the same thing. Okay, I'm gonna pick 30 cookies from this part again, and then I measure the weight of the cookies. And then I use the formula to calculate the sample mean. And this time, my sample mean will be equal to 48.9. Okay, I'm gonna keep working on it. And then I get like different sample means for each 30 cookies. So what happens? Each samples give you a slightly different mean. Okay, you could see that is really close to the 50 gram. And then after I get this 1000 sample means, either I'm using the table or I'm gonna plot this sample means onto the graph. And I will get the sampling distribution of sample means. Okay, I need you guys understand what is the meaning of the sample distribution of sample means. Okay, now look at the definition of the sampling distribution. Sampling distribution is the probability distribution of a sample statistic that is formed when sample of size n are repeat taken from a population. If the sample statistic is the sample mean, then the distribution is called the sampling distribution of the sample means. So just like our cookies example, our sample size n will be equal to 30. And then I try to repeat this progress taken from the population. And then I'm gonna write down for each sample means of these 30 cookies. After I repeat this progress 1000 times, I'm gonna get the sampling distribution of the sample means. For these sessions, we'll be focusing on the sampling distribution of sample means. And then for the session 6.4, we're gonna talk about the sampling distribution of sample proportion. Okay, you could do the same example. We could calculate the proportion instead of calculating the sample mean. If the sample statistic is talking about the proportion, then we're gonna call this distribution will be sampling distribution of sample proportion. Okay, so one more time. So this is gonna be entire population, our cookies. And I already know the mean will be 50 gram, standard deviation will be 5 gram. And then I'm gonna draw 30 samples and I calculate the sample mean. So this is gonna be sample 1, sample 2, sample 3. And then I keep working on it until I do have the sample 1000. And then we call this as 1000 sample distribution. And then I write it down. So this is gonna be my sampling distribution of sample means. And then I try to add it all up divided by 1000 because I have 1000 samples in here. And then I find it out the average of the sample means is going to be equal to 50 gram. It will be exactly same with the entire population mean in here. And we have the notation that this is called the mean of the sample means. Okay, the mean of the sample means will be equal to 50 gram. It will be exactly same with this guy. Okay, how about the standard deviation of the all sample means? Okay, we're gonna talk about it for the next 2 slides. Okay, the mean of the sample means will be the same. And then how about the standard deviation of the all sample means? Okay, sampling distributions. We do have a free case in here. This is talking about when n equal to 1. Okay, n equal to 1, the distribution is going to be normal distribution. This is talking about from here. If the original population is normal distribution, when we increase the sample size n, you still got the normal distribution. Okay? With narrower standard deviation, when you increase the sample size from 10 to the 50, my distribution still looks like normal distribution. So this is our case 1. When your original population is normally distributed for any sample size n, the distribution of the sample mean is a normal distribution. Okay, one more time. When n equal to 1 here, this is talking about the original population here is normally distributed. So we don't really care about the sample size because we are looking for the distribution is going to be normal distribution. Okay, case 2. When I have a uniform distribution when n equal to 1, if we increase the sample size from 1 to the 10, then you're going to see that will be approximately normal distribution, right? If I keep increase the sample size from 10 to the 50, then my distribution will be looks like normal distribution. Same idea for the U shape here. When the original population is not normal distribution, if we can increase the sample size, then finally our sample means will be looks like the normal distribution. So that would be our case 2. But we don't have to get the sample size equal to 50. We're gonna say original population is not normally distributed. Then the sample size n has to be greater than or equal to 30. Okay, right? So this is the requirement for the central limit theorem. Either original population is normally distributed, so we don't care about the sample size. If original population is not normally distributed, then we request the sample size n has to be greater than or equal to 30. Okay, so one more time. Sampling distribution of the statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. Okay, this is specific talking about the statistic. Okay, it can be the mean or it can be the proportion. And for these sessions, we're focusing on the sample mean. Sampling distribution of the sample mean is a probability distribution for all possible values of the random variable computed from a sample size n from a population with the mean and the standard deviation. Okay, just like our cookies example, we know the mean, we know the standard deviation. And then we're gonna choose the sample size n equal to 30. Okay, condition for the central limit theorem for the sample means. So first, it has to be simple random sample and independent. Okay, each sample should be independent on each other. Second, either original population distribution is normally distributed or sample size has to be greater than 30. Okay, this is gonna be the condition if you want to apply the central limit theorem. Okay, central limit theorem. You're gonna see the notation. Remember this guy? This is called the mean of the sample mean. It won't change, just like our cookies example. For the standard deviation for the sample means, you'll be using the population standard deviation divided by square root of n. Let's go back from here. So how can we calculate this guy? We'll be using this formula. Okay, we do have population standard deviation equal to 5, and then the sample size n equal to 30, right? We take n equal to 30 for each time, and then you're gonna calculate it. So that will be your standard deviation of the sample means. So remember the condition, and then remember how to find the mean of the sample means and the standard deviation of the sample means in here. Okay, try this example together. Suppose that the mean time of an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. Write the distribution. So you're gonna see this X bar. This is represent the sample length distribution of the sample mean. And then we need to calculate these two guys. All right, just like here. So first, I know that my population mean that will be equal to 11.4 minutes. And then I know my standard deviation is 3.2. And they didn't give us the sample size yet, so I just keep it as an n in here. And then B, if a random sample of n equal to 35 oil change is selected, describe the sample length distribution of the sample mean 1 to 2 decimal space. So for the question here, they never mentioned about the original population distribution, right? But since we do have the sample size greater than 30, right? So we could apply the central limit theorem. The mean doesn't change, and the standard deviation of the sample mean will be equal to this guy. So we already know population standard deviation, that is equal to 3.2. And then sample size, that will be equal to 35 in here. Okay, use your calculator. You should get 0.54 here. And then C, if a random sample of n equal to 35 oil change is selected, what is probability the mean oil change time is less than 11 minutes, 1 to 4 decimal space? Okay, so we have the mean, that is 11.4. So that would be the highest point in here, that would be 11.4. And then we want to find it out. The mean oil change time is less than 11. So I would assume that 11 is somewhere like here. And then we are looking for the probability, means we're looking for the area less than 11 minutes. Okay, so work it out. We will have probability that x less than 11. Okay, we are looking for the area to the left. And since we're looking for the area, we'll be using normal CDF. The lower point, that will be negative 1e99 until at this point, which is going to be 11. And then your mean, and then your standard deviation of the sample means here. Okay. I don't recommend you guys plug in the 0.54 here. I will just plug in the whole thing on your my calculator. Okay, let's try to do it together. So go to second, VAS, normal CDF, number 2, negative 1e99. Negative, make sure you guys use the 1 under the 3. Negative 1. E will be the comma here. So second comma 99 until 11 comma and then 11.4 comma. And then we're gonna do 3.2 divided by square root of 35. Close. Enter. So you're gonna get 0.2298. Okay, 1 to 4 decimal space. Okay. So the area, which is, so the probability of the mean oil change time less than 11 minutes, so this part of the area will be equal to 0.2298. Okay, example 2. The length of time taken on the SAT for a group of students is normally distributed with the mean of 2.5 hours and a standard deviation of 0.25 hours. A sample size of n equal to 60 is drawn randomly from the populations. So first, I need you guys verify the conditions. You do have the two conditions, right? First one, simple random sample and independent. Okay, they just say like draw randomly from the population, so we could put like simple random sample. And even though they didn't mention about the independent, we'll be assuming the question will fulfill this requirement. And then number 2, original population distribution is normally distributed. Okay, they mention it in here. The group of the students is normally distributed. Okay, so that's why I put it here. Or sample size has to be greater than 30. The sample size is 60, so this is good enough. If they never mention about the original population is normally distributed, you could just ignore this part. Just put the sample size has to be greater than or equal to 30. Okay, now B. Find the probability that the sample mean is between 2 hours and 3 hours. So we write down the mean of the sample mean. It doesn't change, right? It's still 2.5 hours. And then we're gonna find out standard deviation of the sample mean. So plug it in. Standard deviation will be 0.25 hours. Sample size will be equal to 60. Okay, right? And then we want to find out the area between 2 and 3. So 2 and 3 somewhere like here. Okay, we're looking for the area in the middle. So we want to find the area, we'll be using the normal CDF. And also, I need you guys write down like this way. Okay, the x, that will be in between 2 and 3 here. Equal to normal CDF, 2 lower value, upper value will be 3, and then the mean, and then the standard deviation. One more time, try to plug in the whole thing on your calculator. So you should get equal to 1. Okay, so that means the area in between 2 and 3 is almost like take out everything here. Okay, so the picture is not really good. I should put like 2 is up somewhere like here, 3 is somewhere like here also. Okay, example 3. In a recent study report October 29, 2012 on the Florida block, the mean age of the tablet user is 34 years. Suppose the standard deviation is 15 years. Take a sample of size n equal to 100. So verify the conditions. We assume there will be simple random sample and independent. And then condition 2, they never mention about the original population distribution, right? But they do have the sample size that's greater than 30. So I'm gonna put only this part, sample size n greater than or equal to 30. Okay, B. What are the mean and the standard deviation for the sample means age of the tablet user? So the mean, it doesn't change. It's still equal to 34 years in here. And then we're gonna calculate the standard deviation for the sample means. Try to plug it in. Population standard deviation will be 15. Sample size, that will be equal to 100. Okay. Okay, C. What does the distribution looks like? Since the sample size is going to be greater than 30, right? So we will be assuming the distribution will be approximately normal. Okay, D. Find the probability that the sample mean age is more than 30 years. 1 to 4 decimal space. So the mean in the middle here, there'll be 34. So I assume 30 is somewhere like here. Okay, and then we are looking for the probability that is more than. So we're looking for the area to the right. So x greater than 30. Okay, greater than means we're looking for the area to the right. And then we'll be using the normal CDF. So lower value starting for this point with 30, upper value that'll be 1D99. And then we have the mean, and then we have the standard deviation of the sample means. Use your calculator. You're gonna get 0.9962. Okay, Yi, find the 95 percentile for the sample mean age. So this time we'll be given the area. 95 percentile, talking about area from the left is going to be 0.95. And then we want to find out what is your x in here. X will be equal to inverse norm. When they given the area, they want to find out the x. That will be inverse norm, area from the left, the mean, and then the standard deviation. So you should get 36.5 years. Okay. So for these sessions, I need you guys remember the condition for the central limit theorem. And then what is the difference between session 6.2 and session 6.3? Session 6.2, we are working on the sample size n is equal to 1. Okay, if you review the notes from the session 6.2, we do have the similar questions. Okay, just like this one. But at that time, will be mentioned about find the probability that a randomly select A. So n equal to 1. We don't need to apply the central limit theorem. Right? And for these sessions, it's always talking about the n is going to be greater than 1. Okay, that's it.